The dry concrete channel running through the South Saskatchewan basin hasn't carried a drop since March. Not a trickle, just a chalky white mineral crust along the bottom where the salts dried and cracked into patterns like shattered porcelain. Consider this single verifiable anomaly. On a single Tuesday morning in mid-July, 3 separate automated monitoring stations across the Prairie provinces recorded groundwater head drops exceeding 2 full meters in under 6 hours. Not one of those stations triggered a regional emergency alert, because not one of those drops was caused by a sudden seismic shift or a sudden infrastructure breach. There was no main shock. There was no sudden pipe burst. Instead, what unfolded across the western basin was the quiet, simultaneous collapse of an underlying hydrostatic system, a level of regional drawdown not seen in Western Canada since 1936, a year when the Gardner Dam did not yet exist and Lake Diefenbaker was nothing more than a theoretical line on a geological survey map. To understand what is happening right now, we have to execute a precise correction. The national media headlines call this a simple prairie drought. They frame it as a temporary weather anomaly, a hot summer that will eventually be washed away by next winter's snowpack. That loose framing is entirely wrong. What we are witnessing is not a temporary lapse in rainfall. It is the structural depletion of an ancient, non-renewable aquifer system that underpins the entire agricultural and urban economy of the region. The accurate story is far more dangerous and far more compelling because it is a story of legal overallocation, structural subsidence, and an invisible countdown clock ticking down toward a hard physical limit. The fundamental question this entire episode answers is straightforward. When a continent's most vital surface rivers are over-allocated by law, and the deep underground reserves backing them up are drained to the point of structural collapse, which major metropolitan area reaches the end of its water security first? To answer that, you have to look past the superficial headlines and examine the actual physical mechanism. For over a century, the urban centers and agricultural corridors across the Western Plains have operated on a fundamental illusion. When surface water from glacier-fed rivers thinned out during dry cycles, municipalities and commercial operations did what human societies always do. They drilled deeper. They tapped into deep, confined aquifers, ancient groundwater trapped in layers of porous rock and sand, deposited during the retreat of the Laurentide ice sheet over 10,000 years ago. This is not surface water that recharges with the spring melt. It is fossil water. When you pump fossil water out of a deep aquifer at a rate thousands of times faster than natural recharge, the pore pressure within the underground geological formations drops precipitously. The weight of the overlying rock and soil, the overburden, compresses the empty spaces where the water once sat. The silt and clay layers collapse in on themselves. This is subsidence. Once that clay matrix compresses, the physical capacity of the aquifer is lost forever. You do not get a refill when the rains return. You lose the storage tank itself, permanently. Convert the scale of this drawdown into something you can picture. Across the western basin, the volume of groundwater extracted without replenishment over the last 25 years exceeds 35 cubic kilometers. That is enough water to submerge the entire surface area of the province of Nova Scotia under half a meter of standing liquid, or to drain the annual flow of the Bow River straight into a vacuum 3 times over. And while the public gazes at the obvious visible warning signs, shrinking mountain glaciers at the Columbia Icefield and exposed mudflats at major reservoirs, the real crisis is happening underground, completely out of sight. Across the continent, over 40 million people depend on interconnected transboundary river systems and the subsurface aquifers that buffer them. In the Canadian context, Natural Resources Canada and the Geological Survey of Canada monitor these subterranean shifts through specialized satellite gravimetry and deep well networks. But the legal framework governing these waters was drafted during one of the wettest historical periods on record. Governments carved up water rights based on inflated annual flow volumes that the climate simply does not deliver on a permanent basis. They wrote legal checks against a hydrological bank account that was never that full. And yet, municipal leaders continue to approve massive industrial projects, sprawling master plan subdivisions, and high-tech infrastructure like massive server data centers that consume millions of liters of cooling water daily, all directly on top of aquifers that are actively losing structural integrity. Prosperity and physical depletion are running down the exact same track, at the exact same speed, toward an absolute wall. So how do you know when this system reaches its breaking point? You do not wait for a dramatic public announcement. Instead, keep your eye on three specific, verifiable indicators over the coming months. First, monitor the official operational advisories issued by Natural Resources Canada and provincial regulators regarding wellhead pressure thresholds in key regional aquifers. Second, watch for reports of structural earth fissures or localized ground subsidence near major municipal pumping fields along the southern transport corridors. Third, track the formal interprovincial negotiations regarding mandatory flow allocations under transboundary water agreements as seasonal river levels drop toward critical intake elevations. Until those thresholds are crossed, the official posture will remain one of managed calm. But beneath the surface, the physical math is already catching up to the promise. The dry channel in the Western Basin is not an isolated casualty of a hot summer. It is the opening frame of a process that is moving silently toward the taps of millions who still believe their supply is bottomless. On the morning of November 24, 1922, 22 men sat in a wood-paneled room at the Bishop's Lodge in Santa Fe, New Mexico, to sign a document that would dictate the fate of North America's driest corridors for more than a century. The document was the Colorado River Compact. The delegates, representing 7 states and operating under the oversight of federal commissioners, believed they were dividing a perpetual fortune. They looked at river gauge data collected along the basin over the preceding 2 decades and calculated that the river carried an average annual flow of 21.6 billion cubic meters, or roughly 17.5 million acre-feet, of water every single year. They were wrong. Not by a small rounding error, but by a margin so massive it altered the trajectory of an entire continent. The initial framing of that era presented the treaty as a triumph of modern engineering and legal foresight. The headlines declared that the West's water distribution was officially solved forever. But here is the critical correction move that sharpens that historical myth into the far more interesting and terrifying reality. Those early 20th century engineers did not measure a normal river. Unbeknownst to them, the period between 1905 and 1920 was the single wettest 15-year stretch in the entire 1,200-year tree ring record of the North American interior. The baseline they built an empire upon was a statistical ghost. The true long-term average flow of the river system was not 21.6 billion cubic meters. It was barely 16 billion. And in modern drought cycles overseen by monitoring agencies like the Geological Survey of Canada and Natural Resources Canada, transboundary flows consistently dip below 12 billion cubic meters. The architects of the compact did not divide actual water, they divided paper water. They wrote legal checks for 18.5 billion cubic meters of annual guarantees against a river that regularly delivers less than 3/4 of that amount. Every farm, every hydroelectric dam, every municipal intake pipe built across the basin since 1922 has been drawing from an overdraft account that was bankrupt before the ink was even dry. To understand how this structural deficit expanded into a multi-billion-dollar systemic crisis, you have to look at how cities and agricultural hubs adapted when the surface water inevitably fell short. In places like the agricultural valleys outside major regional hubs, farmers in the 1950s could punch a narrow well casing into the earth just 27 meters deep and strike ice-cold groundwater that gushed to the surface under natural artesian pressure. A child could dip their feet into an irrigation canal fed by aquifers that took 10 millennia to accumulate beneath the bedrock. By 1980, as surface allocations thinned under federal rationing agreements, industrial agriculture and rapid suburban sprawl escalated groundwater pumping to unprecedented levels. The historical baseline vanished. Deep turbine pumps were lowered from 27 meters down to 120 meters, then 180 meters. By the late 1990s, heavy pumps were sucking air by midsummer, operating at depths exceeding 300 meters, far below the local water table's capacity to naturally recharge. The physical mechanism driving this collapse is elegant and relentless. Aquifers are not underground caverns. They are saturated layers of sand, gravel, and porous rock intercalated with heavy clay bands. The fluid pressure of the water occupying those microscopic spaces actually supports the physical weight of the sediment above it. When you extract that ancient water, the pore pressure drops to zero. The immense weight of the overlying strata crushes the empty clay matrices flat. This process, known as inelastic compaction, causes the land surface above to sink in direct proportion to the volume lost. Between 1950 and the early 2000s, land elevations in heavily pumped basins collapsed by more than 5.5 meters. Giant earth fissures, vertical fractures reaching depths of 15 meters and spanning several kilometers, unzipped the terrain, severing regional highway corridors, cracking concrete bridge abutments, and snapping subsurface pipelines. Convert this volume loss to something tangible. The volume of groundwater pulled from these subterranean reserves over a 50-year period equals more than 49 billion cubic meters. That is more water than the entire active storage capacity of Lake Mead when filled to the brim at elevation 375 meters above sea level. It is equivalent to draining the total volume of Lake Ontario down by several meters, evaporated completely into the atmosphere through agricultural spraying and municipal usage. When surface water was legally overcommitted in 1922, it set off a chain reaction that forced municipalities into a subterranean arms race. The design assumptions of the early 20th century calculated that groundwater would serve as a permanent, bottomless reserve bank. But a bank account without deposits eventually hits absolute zero. As we look toward the modern baseline, the warning signs are no longer confined to historical charts or dry rural canals. To know whether this historical overdraft is about to force an immediate structural shutdown of downstream urban allocations, you must track three checkable metrics. First, observe whether the Bureau of Reclamation's official 24-month study projects elevation at Glen Canyon Dam to drop below the critical 1,063-meter power pool threshold before December 2026. Second, watch for formal hydrologic advisories from transboundary water commissions regarding mandatory cutbacks in primary municipal allocations. Third, monitor whether regional monitoring wells report a sudden acceleration in compaction rates along major transportation infrastructure. Until those lines are crossed, the historic math continues its quiet, invisible erosion of the grid. A single pale line painted across the vertical rock face of a reservoir canyon, that single strip of white mineral crust is the entire story. At 8 a.m. on July 18, 2022, telemetry sensors at Lake Mead recorded a surface elevation of 317.3 meters above sea level. That single number was not just a historic low, it was a structural boundary line that triggered a cascade of physical and operational failures across the entire continental water network. When news outlets reported on this drop, the narrative focused almost entirely on the surface visuals. Exposed boat ramps, stranded docks, and dramatic aerial footage of shrinking shorelines. But here is the critical correction move that sharpens that superficial narrative. The danger of a falling reservoir is not that the water looks low on camera. The true, far more interesting mechanism is what happens down inside the dam's intake architecture when the water drops below key engineering thresholds. To understand the physical breaking point, you have to look at how hydroelectric and municipal intake infrastructure actually functions. A major dam is designed to operate within a specific hydraulic envelope. At Hoover Dam, water enters through massive cylindrical intake towers located on the upstream side. When the surface elevation sits at its historical normal of 365 meters, the sheer hydrostatic pressure of the water column forces thousands of tons of fluid through heavy penstocks straight into the Francis turbines, generating millions of kilowatt-hours of clean electricity for the grid while pushing regulated volumes downstream. However, if the reservoir surface drops down toward 290 meters, a point known as dead power pool, the water column loses the hydrostatic pressure required to turn those massive turbines. The dam keeps standing perfectly intact, but it completely stops generating electrical power. Even worse is what happens if the surface drops down to elevation 273 meters. Absolute dead pool. At absolute dead pool, the water level falls completely below the physical invert elevation of the lowest intake gates. The fluid stops moving entirely. The river downstream simply ceases to flow out of the structure. The dam transforms overnight from a vital hydraulic engine into a massive concrete wall holding back a stagnant, inaccessible pond. This is where advanced space-based monitoring networks step into the story. To track this invisible loss of mass across North America, scientists rely on NASA's GRACE and GRACEFO twin satellite missions, instruments that measure microscopic fluctuations in Earth's local gravitational field to detect changes in underground water mass. Combined with ground-based monitoring networks overseen by agencies like the Geological Survey of Canada and Natural Resources Canada, the data revealed an alarming reality. Between 2004 and the mid-2020s, the transboundary river basin lost over 49 cubic kilometers of total freshwater storage. Crucially, satellite gravimetry confirmed that 3/4 of that missing mass did not come from the surface reservoirs that everyone was photographing. It was quietly sucked out of deep, unmonitored aquifers beneath the soil. Translate that loss into scale. 49 cubic kilometers of lost groundwater is equal to more than 49 trillion liters of water. That is more than the entire storage capacity of Lake Mead at full volume, or enough to completely drain the annual flow of the South Saskatchewan and Bow River systems combined, leaving an entire agricultural province entirely bone dry. When surface supplies dried up, municipalities and industrial operations punched deeper wells, relying on high-capacity electric turbine pumps operating around the clock. But as the underground water table dropped by over 30 meters in key basins, the physics of extraction shifted violently. Pumping water from 200 meters down requires exponentially more electrical energy than pulling it from 30 meters. This created a compounding systemic feedback loop. As the water level dropped, energy consumption soared, precisely while the hydroelectric dams responsible for powering those massive grid pumps were losing their hydraulic head and generating less electricity. The historical models built by early hydrologists completely failed because they assumed two false premises: that surface runoff from snowpack would remain stationary across multi-decade cycles, and that deep groundwater would act as a non-compressible infinite backup. In reality, the physical mechanism of inelastic compaction destroyed the underground storage capacity, while warming regional temperatures caused a massive portion of the winter snowpack to sublimate directly into dry air before ever reaching the river channels. The evidence of this shift is confirmed by precise GPS baseline stations tracked by geological survey networks. Continuous GPS stations located near regional agricultural centers show the ground surface actively dropping by up to 15 centimeters per year, a direct physical signature of an underground structure collapsing under its own weight. To know whether this breaking point moves from a slow hydraulic collapse into an acute municipal emergency, there are 3 checkable metrics to track immediately. First, watch the official bi-weekly elevation reports from the Bureau of Reclamation to see if Lake Mead dips back toward the 300-meter threshold. Second, check whether Natural Resources Canada issues new satellite-based subsidence warnings for transboundary agricultural basins. Third, watch for formal announcements regarding mandatory power generation cutbacks at major hydroelectric facilities along the river corridor. Until those critical markers are crossed, the grid continues to operate on borrowed hydraulic time. At 14:15 p.m. on June 12, 2023, automated telemetry sensors along a major regional transit highway registered a sudden 40mm offset in the concrete bridge deck over a dry river channel. There was no earthquake recorded by the Canadian Hazards Information Service, no explosion, and no severe storm. The highway was closed instantly by transportation crews because the earth beneath the bridge pilings had simply unzipped, dropped, and sheared the steel support pins clean off. When news outlets cover these events, they treat them as isolated infrastructure mishaps, a bad piece of asphalt, or an aging bridge abutment. But here's the critical correction move that sharpens that superficial framing. This is not a story about road maintenance. What happened beneath that highway was the physical manifestation of deep differential compaction, a direct, real-world consequence of a subterranean reservoir being drained past its absolute structural limit. When an aquifer collapses, the ground surface does not drop evenly. Sandy strata compact at one rate, while thick clay formations compress far more drastically. This differential settling tears across the landscape like a shear wave in slow motion. In agricultural zones across the western interior, this process is unzipping farm fields, snapping buried gas mains, and shearing off deep municipal well casings at depths of 150 meters below the surface. Translate the scale of this ground shift into something immediate. Across the southern agricultural corridor, over 12,000 square kilometers of terrain, an area larger than the entire landmass of Prince Edward Island, is actively dropping by up to 15 centimeters every single year. The total volume of pore space permanently destroyed beneath that single zone over the last decade would hold more than 3.2 billion cubic meters of liquid. That is enough water to fill the domestic needs of a city like Calgary or Edmonton for more than 15 consecutive years, vanished permanently from the national water architecture. The real-world impact cascades directly into daily urban life. In sprawling metropolitan sectors where growth has outpaced surface water rights, municipal authorities have been forced to execute emergency engineering interventions. When intake pipes along major surface reservoirs begin sucking air as water levels breach historic thresholds, cities do not simply turn off the taps. They build deeper straws. Consider the engineering response in major desert hubs reliant on transboundary rivers. Municipal water authorities spent over 2.0 billion Canadian dollars to drill a massive 4.8-kilometer intake tunnel through solid rock, straight into the absolute deepest floor of their primary reservoir. They followed it with a $880 million low-level pumping facility designed for one specific purpose: to continue drawing drinking water even if the reservoir surface drops below the hydroelectric intakes and reaches near dead pool status. Think about what that infrastructure represents. A major city spent nearly $3 billion on civil engineering, whose sole function is to draw the very last remaining drops out of a dying body of water. That is not long-term planning. That is a metropolitan area bracing for impact while continuing to issue residential building permits on top of a drying footprint. Meanwhile, in rural communities, the crisis reaches ordinary homes without warning. A homeowner wakes up on a hot August morning, turns the kitchen tap, and hears nothing but a hollow cough of compressed air as the submersible pump 100 meters below burns out in dry gravel. Replacing a private residential well that has gone dry now requires drilling down past 300 meters, a process costing individual property owners upwards of 45,000 Canadian dollars, with zero guarantee of hitting a viable water table. And the pressure is compounding from new, hyper-intensive industrial consumers. Server data centers, expanding rapidly across the interior to support global digital infrastructure, each consume between 3 million and 19 million liters of fresh water daily just to cool their processing units through evaporative towers. A single large data complex burns through as much municipal water in a single summer month as a town of 40,000 residents consumes across an entire year, drawing directly from municipal systems that are already operating on emergency transboundary allocations. To track whether this escalating crisis moves from localized infrastructure damage to a full-scale municipal shutdown, watch 3 specific checkable markers. First, monitor whether provincial emergency management agencies issue formal structural advisories for major highway corridors crossing known subsidence zones. Second, track whether regional water districts enact mandatory bans on new commercial connections for high-volume industrial users like data centers and manufacturing plants. Third, watch for official filings from the International Joint Commission or regional river basin councils mandating immediate emergency cutbacks on municipal withdrawals. Until those warnings appear on your phone via the Alert Ready system, the surface continues to sink in plain sight. On December 31, 2026, at precisely 23:59 p.m., the legal operational guidelines governing the distribution of North America's largest transboundary river system will formally dissolve. That single date on an interstate calendar is not a vague projection or a computer simulation. It is a legally binding deadline carved into public law, the exact minute when the century-old rules dividing surface water allocations expire completely. forcing 7 jurisdictions and millions of downstream users into unmapped legal territory. When commentators talk about this legal wall, they usually frame it as a political dispute, a temporary disagreement between regional governors and corporate lawyers over water rights. But here is the critical correction move that sharpens that superficial narrative. The coming deadline is not a negotiation about political compromises. It is a hard physical collision between written law and unyielding hydrology. The accurate story is far more serious, because you cannot litigate more rain into existence, and no court order can force a dried-up clay aquifer to expand back to its original volume. What is clearly established by decade-long telemetry from the Geological Survey of Canada, Natural Resources Canada, and satellite gravimetry networks is that the era of relying on non-renewable fossil groundwater to cushion surface deficits is over. The subterranean storage capacity across key western basins has been permanently destroyed by inelastic compaction. When the pore space collapses, the storage tank vanishes. That part of the physics is settled, measurable, and completely irreversible. What remains genuinely unresolved, and this is the precise boundary where responsible science stops and speculation begins, is how fast municipal supply systems will react when surface allocations are cut by 20 to 30% in a single renegotiated agreement. We do not know whether municipal conservation efforts can bend the consumption curve fast enough to stay ahead of reservoir declines, or whether sudden drops in hydrostatic head will trigger catastrophic failure at secondary intake facilities. To know which way this crisis turns as the legal clock expires, there is a specific checkable watch list of 3 developments you can track yourself over the next 12 months. First, watch for whether the International Joint Commission and Transboundary River Basin Councils issue a formal declaration of extraordinary emergency cutbacks before the December 2026 deadline. Second, monitor the official bi-monthly reports from the Bureau of Reclamation to see if Lake Mead's surface elevation breaks below 300 meters, which would force the immediate shutdown of primary hydroelectric turbines. Third, track whether provincial regulators in Canada issue mandatory pumping caps on commercial and industrial wells along the southern Prairie agricultural corridor to protect remaining drinking water tables. Until one of those 3 markers is breached, the situation remains precisely what the physical measurements show: a massive, highly complex continental water grid running on its absolute lower limits, where a single dry winter or unexpected infrastructure breach will transform a long-term resource deficit into an immediate municipal emergency. The dry canal running through the Western Basin was never an isolated regional anomaly. It was the quiet opening scene of a continental system finally running out of borrowed time. Let us know in the comments below which region or community you are watching from. Subscribe to stay updated as we continue tracking the physical data behind North America's most critical resource shifts.